In this section, we're going to do an introduction to hypothesis testing. So first, let's review inference. Statistical inference is when we use the information about the sample to learn about the population. So we have our population parameter, we take a sample, we get a statistic, and we try and then estimate or conclude something about a population. So confidence intervals let us estimate the value of the parameter. That's very useful. Hypothesis tests let us say, is the parameter greater than some proposed value? Okay, so is my population mean greater than 8, or maybe less than 8, or different from 8, or whatever it might be. We might also do this if we want to know if a proposed population value is plausible or not, or maybe we want to know if a difference is significant or just due to chance. So let's recall our steps of statistical investigation from section 1.1.2. We had to ask a statistical research question, collect the data, then analyze the data, and then draw conclusions. But in step 3, to analyze the data, we use summaries of the data and statistical methods to identify patterns, trends, unexpected outcomes. And one of the things we said that we do is we want to see if observed effects are real or just due to chance, and then estimate their size. Well, estimating their size, that was confidence intervals. So that's confidence intervals. And we learned how to do that. But trying to decide if something is real or just due to chance, this is hypothesis tests. This is what we're going to learn now. Hypothesis tests are used all the time in every different field that you can think of. So let's start by looking at the logic of it. So let's say we have a damaged coin and we're wondering if it is still fair or if we're getting too many heads. We toss the coin 100 times and get 53 heads. Okay, sounds like it's probably fair. Doesn't sound too off. But let's, instead of just saying, based on what we think our gut is saying, let's figure out how to quantify this. So we can estimate the population proportion of heads, P, with our sample proportion, P hat. Let's assume that our coin is fair. So if the coin was fair, we could claim that the population proportion of heads is P equals 0.5. Now, if we were to toss a fair coin, so we are assuming now that the coin was fair, we would expect to get, if we do it 100 times, we'd expect to get about 50 heads, give or take what? Well, how do we do that? We would do the expected value of P hat. So what's the expected value of a sample proportion? It's just equal to the population proportion P, so 0.5. And what's the standard error of P hat? That's the square root of P times 1 minus P over N. Now, we've been doing P hats on our confidence intervals because we didn't know what P is, but we are going to assume that P equals 0.5 for all of these calculations. So we can actually use that population proportion that we are assuming. So the square root of 0.5 times 1 minus 0.5 all over N, and N would be 100 in this case. So 0.5 times 1 minus 0.5 over 100, take the square root of all of that, we get 0.05 as a proportion. So if I want the number of heads, it would be 5 heads. So if we toss the fair coin 100 times, we expect to get about 50 heads, give or take 5 heads. Now, so based on that fact, if I expect to get about 50 heads, give or take 5 heads, would you be surprised that we actually got 53% heads, or 53? I would say no, because that's certainly within 50 plus or minus 5. Okay. But now let's quantify that a little bit more of how many standard errors was our observed value from our expected value. Because remember, we're going to say we're surprised if we're more than 2 standard errors away from what we expected. So could you explain that difference of how far we were by just chance error? So in section 8.1.2, we learned that the z-score tells us how many standard deviations or standard errors a value is from the expected value. Since P hat is our estimate P, we could rewrite it as Z equals our estimate minus the expected value of the estimate over standard error. So in our case, our estimate was our actual P hat of 0.53. So it'd be P hat minus the expected value of P hat over the standard error of P hat. So 0.53 minus the expected value, which was 0.5, divided by 0.05, which gives me 0.6. So we were only 0.6 standard errors from what we expected. So we were only 0.6 standard errors from the expected value. Okay, that is not surprising at all. So remember, you have to be more than 2 standard errors to be surprised. Well, if the coin was fair, what is the chance that we could get 53% heads or more? So here's the sampling distribution of all the possible sample proportions we could have gotten from a sample size of 100 if the population proportion was really 0.5. Okay, so here's my sampling distribution. I would have expected it's centered at 0.5. So here's my centered at p equals 0.5. I got a sample proportion of about 0.53. So what's the chance that I could have gotten a 0.53 or more? We always go out to say more extreme, as anything more suspicious, we include that as well. So what's the chance I got a 0.53 or more? If you look at that, it looks really big, right? So we want to find the chance that we'd pick a sample that had a sample proportion of 0.53 or more. Because we standardized our data, we found the z-score, we can use the standard normal curve to find probabilities. So looking at this, z equals, what was our z value? Z equals 0.6, and I'm looking for the area to the right of that. So this is going to be p norm of 0.6, and I want the upper tail, so I'll do the lower dot tail equals false. And if I put that into r, I should get about 0.274. So we could say something like, if the coin was fair, there was a 27.4% chance that we could get 53% heads or more. Okay. So, do you doubt that the coin is fair? No. The coin is probably fair. Or there is no reason to think that the coin was not fair. So no reason to think that it was not fair. I know that is a double negative, but we're going to write all of our answers with double negatives like this. So now let's try a different coin. We're going to toss it 100 times. Heads come up now this time 63 times. Could the difference between what we got of 63 heads and what we expect of the coin's fair of 50 heads be due to chance error? Or is there something wrong with our coin? And when I say chance error, I just mean every time you take a sample, you get different results. Every time you flip coins, you get different results. And the chance error is just that variation from sample to sample. Okay. Or is there something wrong with our coin? Is the chance of heads more than half? So let's assume that our coin is fair. I'm going to claim that my population proportion of heads is 0.5. Now, if we toss a fair coin 100 times, we'd expect to get about 0.5 heads, give or take. So this is the expected value of p hat. Give or take the standard error of p hat, which we calculated up above was 0.05. So see up above. Are you surprised that we actually got 63%? Okay, so if we say it's supposed to be 0.5, give or take 0.05, we're getting 0.63, be surprising? That's looking like it could be a bit more surprising. So let's go and calculate how many standard errors was our observed value from our expected. Could we explain that difference between our observed and expected values by chance error? So our actual estimate that I got, that's my p hat, minus the expected value of p hat over the standard error of p hat. So my estimate of p hat was 0.63 minus the expected value of 0.5 over the standard error, which was 0.05. That gives me 2.6. Okay, this is more than 2 standard errors away. So we're 2.6 standard errors away from what we expected. So this is surprising. Okay, let's go a step farther and see what is the chance that that would actually happen. So if the coin is fair, notice I am saying a big if there. If the coin is fair, what's the chance that we get 63% or more heads? So here's our sampling distribution. For 0.63, if I want 0.63 heads or more, notice that looks like a very small chance. So we're finding the chance that we could pick a sample that has sample proportion of 0.63 or more. We'll use our z-score in the standard normal curve. So here we had z equals 2.6, and we're looking for the area to the right. So we'll do p norm of 2.6, and my lower dot tail equals false. Now, if you remember, because this was my standard normal curve for z, that's the default in R. That's why I don't have to put in the mean and standard deviation, because it is the default in R. Okay, it knows that the mean is 0 and the standard deviation is 1 for that standard normal curve. When I put it into R, I get a probability of 0.0047. Okay, so we had a 0.0047 chance that we could get 63 heads or more on a fair coin. Okay. So do you doubt that the claim is fair? Yes, absolutely, I'm doubting that. That is a very small chance that it could happen. So what was more likely? Was it more likely that the coin is fair and I just happen to get 63% heads and 100 tosses, which had a chance of 0.0047 of happening? Or do you think that the coin was unfair and the chance of getting ahead is really greater than 50%? I think that the coin was unfair and the true proportion was greater than 50%. So we just did a basic hypothesis test without having to learn anything new. So you already know everything you need to know to do a hypothesis test. Okay, we're just going to introduce a lot of terminology and notation for you. The key idea is that if your observed value is too far away from its expected value, it's hard to explain by chance. Now, scientists or statisticians have come up with hundreds of different types of significance tests for many different situations. We're only going to go over a few of the most basic ones, but they all follow the same format. So I want to repeat this process, but add in some official terminology. So let's say we have one more damaged coin. We think this coin doesn't give us enough heads. So we toss it 100 times and get 35 heads. Let's do a hypothesis test to see if it's fair or if it doesn't have enough heads. So our null hypothesis is always the status quo, whereas the alternative is what I'm hoping to show. So I believe, I'm going to fill out the alternative first. We write it like this, H with a little a for alternative hypothesis. I think that my population proportion is actually less than 0.5. That's what I actually think it is. But my null hypothesis, that status quo, I'm going to assume that it is actually fair. So the null hypothesis, P equals 0.5. So we assume the coin is fair. So we can do some preliminary work if the population proportion really is 0.5. So if the coin is fair. So for all of our calculations, we assume the coin is fair. So we assume the coin is fair. And P equals 0.5. So then my expected value for P hat is just equal to P. So 0.5. And my standard error for P hat, we already did it, but let's just write it down again. So it's going to be 0.5 times 0.5 over my sample size of 100, which still gives me 0.05. So that's the preliminary work of knowing what our expected value and standard error. Now, for my test statistic, we said it's always our estimate minus expected value over standard error. So P hat minus expected value P hat over standard error P hat. Okay, so I could, if I wanted to, even rewrite this as P hat minus the expected value, which is P, over the standard error, which is square root of P times 1 minus P over N. So sometimes instead of doing that preliminary step, you'll just see people go straight to this big long formula, but really it's just P hat minus expected value over the standard error. We've already done the calculations. So P hat, in this case, we got 35 heads out of 100. So P hat equals 0.35. And my sample size equals 100. So we'll do 0.35 minus the expected value of 0.5 over the standard error of 0.05. So this gives me -3. So this is more than 2 standard errors away. So we know we're going to be surprised. Okay. But let's find what's called the p-value, which is that probability. So if the coin is fair, what is the chance of getting a sample with 35% heads or less? We're going to go less this time because less is what would actually be even more extreme. Because we thought that we're getting less heads than we were supposed to. So here's my sampling distribution of what I could have gotten. We want to say what's the chance that we could get 0.35 or less, something more extreme, more surprising. So we want to find the chance that we could pick a sample that has a sample proportion of 0.35 or less. So we're going to go to R and we're going to do P norm of not 0.35. Because we've already standardized it, we're going to use our Z value. So we'll do the -3. Okay. And then we're going to say our lower dot tail equals false. And this should give me 0.0013. Now, could you do it with the actual proportions? Could you say p norm of 0.35, okay, and then put in the mean for my sampling distribution of 0.5 and the standard error of my sampling distribution of 0.05, and then do your lower dot tail equals false? Absolutely. It will still give you 0.0013. But the thing is, once people have gone to the work to find Z and figure out how many standard errors they were, it's a lot easier to just put that into the calculator. Also, before we had calculators, you had to do it that way. So traditionally, every time we do hypothesis tests, we're always going to just put in our Z value because we've already gone to all the work of finding that, instead of using all the values from our sampling distribution. So my p-value, that chance of it happening, was 0.0013. So as p-value, this is if the coin is fair, what's the chance of getting a sample 35% heads or less? That chance is 0.0013, so not likely at all. So what do you think is more likely? That the coin is fair and I just happen to get 35% heads and 100 tosses, that which had a chance of 0.0013, or that the coin is unfair and the chance of getting heads is actually less than 50%. I think that one is true. So I think the coin was actually unfair. So do you think we should reject or fail to reject the null hypothesis? Coming back up, the null hypothesis was that the coin is fair. I don't think that's true because we had such a small chance of getting what we got if the coin is fair. So I think the null isn't true. So what we're going to do is we say specifically that we reject the null. And we think the population proportion is less than 0.5.